Greetings everyone. We are excited to introduce our project, the Octave Wave Frequency Detector. In the world of musical technology, whether you are building a digital guitar tuner, developing audio software, or just analyzing sound, the core challenge is simple but crucial: figuring out the exact pitch of a sound. Our detector is a tool designed to solve this very problem. My name is Aryan Anand Mayekar, and I am joined by my teammates Archit Langde and Nirja Manjrekar. We are all students in the Electronics and Telecommunication Engineering program at Bharatiya Vidya Bhavan Sardar Patel Institute of Technology, Mumbai. We will walk you through the technical details of this project. Let's start with the challenge. Many devices like digital tuners and audio software need to know the exact pitch of a sound to work correctly. The fundamental problem is that real-world sound is messy. It's full of harmonics, background noise, and reflections, which makes it difficult to isolate the true fundamental pitch that defines the note. Our project, the Octave Wave Frequency Detector, was created specifically to cut through this noise. It's a smart, robust tool built in MATLAB that has a twofold function. First, it uses advanced signal processing to find the main frequency, the core pitch of that sound. Second, it instantly translates this raw frequency into its simple universal musical name, the correct note like C or A, and the octave number like 4 or 5. In essence, we are turning complex sound wave into clear, accurate, and actionable musical information. To achieve our goal, we established 3 primary technical objectives for the project. Objective 1. High quality audio capture. Our first job was to ensure the input was good. We must successfully record sound using the industry standard sampling rate of 44.1 kHz. This high rate is essential because it guarantees a wide and detailed frequency ranges, allowing us to accurately capture everything from low bass to high treble notes. Objective 2. Accurate pitch detection. This is the core engine. We utilize the power of the Fast Fourier Transform, which is the foundational algorithm in digital signal processing, to mathematically determine the signal dominant fundamental frequency, which we call peak frequency. Objective 3. Implement musical mapping. The final step is translation. We had to implement the precise mathematical relationship, specifically using the MIDI formula to accurately map the detected frequency in Hertz to its standard musical note C, D, etc. and its corresponding octave number. Starting with the concept of an octave. An octave is not just an arbitrary name, it's the most foundational interval in music. The definition is simple. Two notes are separated by an octave when the frequency of one is exactly double the frequency of the other. For example, the global standard for the note A in the 4th octave, or A4, is 440 Hz. If we double that frequency, we get 880 Hz, which is precisely the note A5 or A in the 5th octave. The underlying formula is simple. F2 is equal to 2F1. This doubling is what makes the note sound so similar yet distinct. Crucially, in Western music, each octave is divided into 12 half steps or semitones. Our detector's ultimate job is to identify which of these 12 notes and which specific octave range the input sound falls into. It is important to distinguish between two terms we'll be using constantly: frequency and pitch. Frequency is the physical measurement, the number of cycles a sound wave completes per second measured in hertz. This is the raw data our sensor captures. Pitch, on the other hand, is the perceptual measurement. It describes how high or low a sound is perceived by the human ear. This is the musical and usable output, the note name, like AC or G. Our detector bridges the gap between these two worlds. It accurately measures the raw frequency and then calculates the corresponding pitch. The critical step of translation relies on the MIDI standard. To translate a detected frequency into a musical note and octave, we rely on a standard logarithmic formula. Why logarithmic? Because the musical distance between notes is exponential, that is multiplicative. But the system we use to label them, the MIDI node number system, is a linear additive system. The MIDI, Musical Instrument Digital Interface System, assigns a simple integer number from 0 to 127 to every possible musical note. The anchor or key reference that holds the entire system together is the note A4, which is standardized at 440 Hz and assigned the MIDI number 69. Our project uses this fixed reference point and the mathematical formula to reverse engineer the MIDI number from the detected frequency, giving us the correct note and octave. We can break down our system down into 5 logical sequential stages. This is the pipeline of our detector: audio acquisition, time to frequency transformation, fundamental frequency detection, musical mapping and octave calculation, output and visualization. Let's dive into the details of each stage. Stage 1: Audio acquisition. Stage 1's goal is to capture the real-world analog sound and convert it into a clean digital data. In MATLAB, we use the standard audio recorder function. The crucial parameter we set here was the high sampling frequency of 44.1 kHz. Think of the sampling rate as the number of snapshots you take of the sound wave per second. 44.1 kHz is the CD quality standard. This choice ensures excellent audio fidelity, and the Nyquist theorem lets us accurately analyze frequencies up to 22.05 kHz. The output of this stage is simple but vital vector of digital audio samples, a list of numbers representing the sound wave in the time domain. Stage 2: Time to frequency transformation. Stage 2 is the core of our digital signal processing (DSP) engine. Our goal is to convert the time-based audio samples into their individual frequency components. The Fast Fourier Transform takes that complex sound wave and mathematically breaks down into all the individual sine wave frequencies that make it up. The output is the magnitude spectrum. This is a graph that shows us the strength or amplitude of every single frequency present in the sound. Stage 3: Fundamental frequency detection. Now that we have the full spectrum of all frequencies in stage 2, stage 3's goal is to be decisive. Find the single most important frequency that defines the sound's pitch. This is the fundamental frequency. This process is simple but effective. We'll look for the maximum value within the magnitude spectrum. Since the fundamental frequency is typically the strongest component, its peak is the highest on our spectrum graph. We then take the index, that is the position of that peak, which directly correlates to a specific frequency value. This gives us the peak frequency, especially expressed precisely in Hertz. Stage 4: Musical mapping and octave calculation. Stage 4 is where we achieve the core value of the project, translating the scientific Hertz value into a usable musical name. As discussed earlier, we do this by implementing the standard MIDI note number formula, anchored by A4 is equal to 440 Hz. The formula takes the peak frequency we just found and calculates a precise note number, the integer between 0 and 127. We then use a simple lookup table based on that number to identify two things: the correct note name and the corresponding octave number. Stage 5: Output and visualization. The final stage is where our analysis becomes a tangible result. Our goal is to present the core findings clearly and provide visual validation that confirms the accuracy of our detection. We deliver two key outputs. The first one being text output. This is the essential answer. We display the precise detected frequency in Hertz, the corresponding note name like C, F hash or A, and the other octave number like 4 or 5. This output is ready for immediate use in any musical application. The second is visual validation. The three graphs. These plot allows us to visually confirm the entire process. The first one is time domain signal. This plot shows the raw audio data, the simple sound wave. We use it to confirm the quality of the initial recording. The second one is magnitude spectrum. This graph is critical. It shows the strength of every frequency present in the sound and visually highlights the largest spike, which is our peak frequency. The third one is spectrogram. This plot adds the element of time. It visually demonstrates how the frequency content changes over the duration of recording, which is especially useful for verifying that the pitch was stable during the analysis window. Next, we will explain you the MATLAB implementation of this idea.
Allow me to walk you through the code. The first line of code sets the sampling frequency to 44,100 Hz. This is a standard high-quality rate commonly used for CD audio. The next line sets the duration of the recording to 4 seconds. The third line creates an audio recording object whose arguments are the sampling rate, the bit depth, and the number of audio channels. We then display a message prompting the user to start speaking or singing. The fifth line of code starts the recording. This function here pauses the execution of the code until the specified duration, that is of 4 seconds in our case, has passed. We display a second message to indicate that the recording has completed. The seventh line of code extracts the recorded audio samples from our object here and stores them in a column vector named audio data.
I'll explain the second section of the code, that is computing the Fourier transform. The first line n equals to length audio data gets the total number of audio samples n in the audio data vector. nFFT equals to 2 raised to next power 2 of n determines the optimal length for the FFT, that is nFFT. By using the next power of 2 greater than or equal to n, the FFT algorithm runs significantly faster. FFT data equals to absolute of FFT of audio data, comma nFFT calculates the discrete Fourier transform of the audio data using the FFT algorithm, padding it to length nFFT. The absolute function is used to get the magnitude of the complex valued result, which represents the strength of each frequency component. Frequency is equals to 0 to nFFT minus 1 into Fs by nFFT. This line creates a vector of nFFT frequency points, that is f. The frequency resolution is del f equals to Fs by nFFT. This line calculates the frequency for each index of the FFT data from 0 Hz up to Fs minus del f. FFT data equal to FFT data of 1 is to nFFT by 2. The obtains the magnitude spectrum of a real valued signal is symmetric. This line discards the redundant second half of the spectrum from Fs by 2 to Fs. Frequencies equal to frequencies of 1 is to nFFT by 2 truncates the frequencies vector to match the shortened FFT data vector, so it now ranges from 0 Hz to just below a sampling frequency by 2, that is the Nyquist frequency. Then the next section of the code is about finding the peak frequency. So this line finds the maximum value in the FFT data, the peak, and returns its index, that is peak IDX. The tilde discards the actual maximum magnitude value as it's not needed. Peak frequency equal to frequencies of peak IDX uses the peak IDX, that is peak index, to find the corresponding frequency in the frequencies vector. This is the fundamental frequency of the sound, often determining the perceived pitch. Then the third section of the code is about identifying the corresponding musical note and octave. If A4 frequency equals to 440 defines the reference frequency for the note A4. Then note names equals to A sharp, B, C sharp, D sharp, E, F sharp, G sharp. Creates a cell array containing the 12 note names in an octave starting from A. Then semitones from A4 equals to 12 into log 2 of peak frequency upon A4 frequency, that is reference frequency. Calculates the exact number of semitones n. The peak frequency is away from A4 using the musical interval formula n equals to 12 log 2 of F1 by F2. Nearest semitone equals to round of semitones from A4 rounds the exact semitone value to the nearest integer to find the closest note in the standard 12-tone scale. Note index equal to modulo of nearest semitone, 12 plus 1. Calculates the index or position of the note within the 12-note cycle. Mod of n comma 12 results in an index from 0 to 11. Adding 1 makes it one base, that is 0 to 12, for use with the note names array. Musical note equals to note names in curly bracket note index retrieves the musical note name, example C, G sharp, from the note names array using the calculated note index. Octave number equals to floor of nearest semitone plus 9 by 12 plus 4. This calculates the octave number. This formula relates the total semitones from A4 to the standard octave numbering scheme, where C4 starts octave 4. It is based on the fact that C4 is 9 semitones below A4. That is, nearest semitone is equal to minus 9 at C4. Then fprintf detected frequency, comma peak frequency prints the calculated fundamental frequency to the command window. Fprintf corresponding octave, comma octave number prints the calculated octave number. Fprintf detected musical note, comma musical note octave number prints the combined musical note and octave. Then coming to the section 4, it is about plotting the audio signal in time domain. T equals to 0 to n minus 1 divided by sampling frequency creates a time vector t for the x-axis of the plot. It contains n points starting at 0 and ending at n minus 1 by fs. Figure creates a new figure window for the plots. Subplot 3,1,1 creates a grid of plots, that is 3 rows, 1 column, and selects the first position for the current plot. Plot T, audio data plots the audio data, that is amplitude, against the time vector t. Title time domain signal sets the title of the first plot. X label time in seconds labels the x-axis as time in seconds. Y label amplitude labels the y-axis as amplitude. Grid on adds a grid to the plot for better readability. The fifth section is about plotting the frequency domain. Subplot 3,1,2 selects the second position, that is the middle plot in the 3:1 grid. Plot frequencies, FFT data plots the FFT data, that is magnitude, against the frequencies vector. The highest peak corresponds to the peak frequency. Title magnitude spectrum sets the title of the second plot. X label and Y label labels the x and y axis as frequency in hertz and magnitude respectively. X limit 0 to fs by 2 sets the x-axis limits from 0 Hz up to the Nyquist frequency, that is sampling frequency by 2. Grid on adds a grid to the plot. Then the sixth section is about playing back the audio. Display playing back your audio displays a message indicating playback is starting. Sound off audio data, sampling frequency plays the audio data using the specified sampling frequency fs. Run this code and see the output. Now I'll start speaking. Hello, I am Neeraja. Now I'll start speaking. Hello, I am Neeraja. This is the output, and the detected frequency is 207.09 Hz. The corresponding octave is 3 and the detected musical note is G sharp 3. These are the figures plotted that are time domain signal and magnitude spectrum.
Overall, this project not only identifies the pitch and note of a recorded sound, but also provides a clear visual representation of audio signals, making it useful for applications in music analysis, voice recognition, acoustic design, and digital audio processing.